I'm Dick Moberg, and for more than 40 years I've been developing technology to advance our understanding of the injured brain. I've had a chance to work with some of the leading minds in the field of neuromonitoring, including physicians, researchers, and entrepreneurs. I want to share their stories with you in the form of a weekly podcast so you can stay current on the latest developments in the field and the innovative people behind them. This is my neural network. So my guest today is Thomas Heldt, and he's the Associate Professor of Electrical and Biomedical Engineering at MIT. And Thomas has a long background in ICP analysis and in particularly in trying to measure ICP non-invasively. So welcome to our podcast.
Thank you, Dick. Thank you very much for inviting me.
So non-invasive ICP is it's been a holy grail for a number of years. I remember back in the 80s, I think I applied for I think NASA was requesting proposals for this, and it just hasn't, I don't think anyone's sort of reached the goal of this, but you guys are making a lot of progress. And maybe you can just tell us a little bit about your take on the history of non-invasive ICP.
Yeah, I mean, it certainly has a long history, and it goes probably back 30, 40 years, as you pointed out. And a lot of people have looked at this problem from a variety of different perspectives. There's, a whole range of prior work where you're trying to deduce changes in ICP from variables, physiological variables that can easily be measured. Whether it's ultrasound time-of-flight measurements across the skull, whether it's evoked potentials, electrocortical potentials, whether it is sort of minute fluctuations in volume in the outer ear, actually. Then there's a whole host of technologies and approaches that were used that use physiological waveform measurements, like arterial blood pressure, cerebral blood flow velocity, measured with transcranial Doppler ultrasound. So magnetic resonance imaging, even with with very detailed fluid dynamic models. The work of Norm Alperin comes to mind, of course, and applying pressure on the eyeball and balancing that pressure or measuring cerebral blood flow velocity in the ophthalmic artery. That's the work of Arminas Ragauskas and others. I mean, Bernhard Schmidt used the arterial blood pressure waveform, cerebral blood flow velocity waveform in a system dynamic approach and identification approach to estimate ICP. So there's a long history, and there's a few review papers for those of your listeners who are interested in that that one can find that review the longer term history of this field. We have added to that literature a little bit over the past 10 years, and we use a model-based approach, meaning that we are using a mathematical representation of the underlying biophysical properties of a major vascular territory in the brain, and how arterial blood pressure and cerebral blood flow velocity as a surrogate for volumetric cerebral blood flow interact with the intracranial pressure, the cerebrovascular properties of that vascular territory. And we formalize that in a mathematical model that represents these relationships. And then we try to solve that model with the input data that we have, namely arterial blood pressure and cerebral blood flow velocity for intracranial pressure, the cerebrovascular resistance, and the cerebrovascular compliance.
Yeah, thanks. I thought in your, so we're at the ICP 2019 meeting, is where we're doing this interview, and I heard a talk from you a couple of days ago where you were giving a little more of a visual representation of what you're doing, where you said you're standing in the artery and looking down there.
Yeah.
Maybe you could describe what you're doing in a non-mathematical way.
Sure.
And just, I'm in the artery looking at it. I thought that was very good.
So imagine yourself standing, within a major vascular segment. So let's say the MCA M1 segment, and you're looking down. into the vascular tree, and as you're looking down in this, complicated branching topology of the vasculature, you see, elastic properties that vary with distance along that tree. You have compliance that changes. Arteries tend to get a little stiffer as you go away from the large arterial segments. And so, and the outside pressure is assumed to be intracranial pressure or some tissue pressure that surrounds the this vasculature. And if you look into down into that vascular tree, and you were to model this, it's a very complicated geometry. It's a very complicated mix of biophysical properties. But it turns out that you could write out very complex models to represent that geometry and that physiology. But it turns out that you can collapse all of this into a fairly simple model that just represents the lumped elastic properties, which will mostly be the elastic properties of the large arterial segments, so the beginning portions of the MCA territory, and then the which is in the surrounding brain tissue. And the cerebrovascular resistance is sort of the lumped resistance that you would see, or that the fluid would actually experience flowing downstream into the smaller and smaller vessels, and finally the terminal resistances. And you can, sum across all of these resistances in parallel and come up with a lumped resistance that just represents that vascular territory, the peripheral resistance of that vascular territory. And the downstream pressure there again is intracranial pressure, which is so that the cerebral perfusion pressure as we know it is the arterial pressure minus the intracranial pressure. So, within some approximations you can turn that very detailed structure and complex biophysical properties, the structure with complex biophysical properties, into something which is tractable in a mathematical sense in terms of the estimation of a single resistance, of a single compliance, and the outside pressure, which is intracranial pressure.
Seems like a very elegant method. And I guess the follow-on question is, where do you see this going? So in the future, I know you're doing some very interesting work, and some other groups are. When do you think we'll have a good measure of non-invasive ICP that can be used clinically?
Yeah, I think that was one of the questions that was, posed to me, by the conference audience, and maybe I in hindsight, I gave it somewhat overly optimistic assessment. Right. But let me actually sidestep the question a little bit. Let me tell you what I think is necessary in order to get there, right? And then we'll figure out what the time frame might be. First, if you think of our particular method as sort of one candidate version, we use the arterial blood pressure measurement, and in the neuro ICU you have that available mostly through radial artery cannulation. So you have a very good and high fidelity measurement. We also use the cerebral blood flow velocity, which is measured with transcranial Doppler ultrasound, and for that you tend to need a skilled operator or someone who has some experience with hitting the right vessel and getting a good signal. So there's one piece to this, to your question, which relates to the development of the appropriate hardware. Ideally, we would like to have a fully autonomous, completely operator-independent way to get the cerebral blood flow velocity. And here at the conference and at the vendor fair, we've seen, some robotic actuation that, goes towards that. But some of these devices still look somewhat clunky and still require a little bit of supervision. So one piece is we would like to have a fully autonomous, operator-independent, easy to use, set it and forget it kind of way to get the cerebral blood flow velocity, and that you switch it on, you can switch it off remotely. That needs to happen. I don't think that that's technologically too far in the future. It's just that the TCD market for the big or the ultrasound manufacturers has always been a niche market. But we hope that changes, because the neuromonitoring needs are not just in the ICU. They're everywhere, whether it's the pediatrician's office, whether it's the ophthalmologist's office, whether it's the emergency department, whether it's the ambulance. So So I think making that point clear to some of the big manufacturers is important. But technologically, I think we can get there fairly expeditiously. A little bit more tricky is the need for the arterial blood pressure waveform, because you do want to have that also non-invasively. And then there are some products out on the market that gives you the waveform, the arterial blood pressure waveform, completely non-invasively. We haven't had great success in using such products in our ICP estimation because the variance in that signal is actually quite large. So another hardware development piece that needs to come together is to get a fully non-invasive, high-fidelity, robust arterial blood pressure waveform measurement. And, colleagues of ours and we are working, towards that goal on a separate project. And then it requires clinical validation. And we need to generate a box that we can give to people, and then put it through the ringer. And what I've presented here at the conference is validation that we've done in the Boston area with colleagues at Boston Children's Hospital, Robert Tasker, Beth Israel Deaconess Medical Center, Ajit Thomas, and at Boston Medical Center with Jim Holtzappel. These are neurosurgery and neurocritical care colleagues. And we presented about 30 patients, age range about 2 to 85, with a variety of conditions: traumatic brain injury, subarachnoid hemorrhage, metabolic disorders, cerebrovascular malformation. So the results so far hold up, but 30 patients is of course not enough. And eventually it will have to go to multi-center, independent validation, and all of that takes time, and patients need to be recruited, consented, and studied. So you've asked me about a timeline. So I guess my best cop-out on that question is that we will try to take, we'll try to de-risk every step along the way and make sure that we understand the problem that we're up against, because even the data collection, for our validation study involved some very non-obvious problems that we had to overcome in order to get to the results that we currently have. But if you really want to know a number, I hope that within the next 10 to 15 years we could be there. At least that we actually have a solid understanding of what the next hurdles might be and where the opportunities are to further optimize the approach from an engineering perspective.
Yeah, well, thanks. That's I guess everybody would want it to be sooner than that, but you're being very realistic, which is good. And I think the result would be that what I've always heard is that we're only monitoring ICP in maybe 20% of the patients that you want to, or I don't know what that percent is, but non-invasive measures would open that up to a much wider patient population, those that you don't want to drill a hole in the head. So I think it's a very significant work that you're doing, and we wish you well for the future.
Thank you very much, Dick. Thank you. I fully agree with you. And one thing that excites me also about this is, of course, to help patients. But we know so little about the biophysics of the cerebrospinal fluid space. We don't understand normal pressure hydrocephalus. I don't think we do. And if we had a non-invasive way to measure intracranial pressure, we get at one of the very key variables that would shed light on a number of conditions, either to rule out changes in ICP or to fail to rule out. So there's also a basic science piece that is going to be very interesting once someone develops a technology like that, where we can learn a lot about conditions that are currently not on our radar screen.
Thank you, and again, good luck. And just one closing anecdote: you are the owner of our very first CNS monitor, serial number 1.
Yeah, we do have that actually. We do have that in our lab, and I actually inherited it, if you can say it that way, from a great mentor and friend, Audrey Duplessis, when he left Boston Children's Hospital. We got it. It stays in my lab, and it literally on the plaque it says 001. Yes. So and I'm a proud owner of that of that unit. So I hope that eventually it will be in the Smithsonian, my friends.
Yes. Well, okay. or at least in our museum, which is a little smaller. But, well, thank you very much for talking to us today, and again, good luck with your work.
Thank you, Dick. It's always a pleasure.
And great, and we'll provide links to those review articles that you mentioned on the website of our podcast. So thanks for listening to this week's podcast. If you enjoy these interviews, please take a moment to rate and review this show on your podcast app of choice. Subscribe to Dick Moberg's Neural Network to receive notifications when future installments are available. Thanks for tuning in, and we hope you'll join us again soon.